Hello, everybody. My name is Chris Ahrens, and today I'd like to discuss climate change and more specifically, the best modeling strategy to predict critical climate change for our planet. Just a little introduction, and I'm sure most of you are already aware, global warming is one of the largest threats to sustainability and survival for life on Earth. So really, since the late 1960s, we've seen an exponential increase in global temperature due to greenhouse gases. And really, the purpose of this project is preserving healthy and sustainable life on the planet by using publicly available global temperature data to predict when the temperature of Earth will reach critical status. Some background research. Really, this project provides both intrinsic and humanitarian benefits to the entire world. By identifying tipping points in the world climate, certain events can be mitigated or even prepared for. Limiting warming to 1.5 degrees Celsius is really the goal we're talking about when we're looking at critical global temperature. Really, since the late 1800s is going to be our baseline for this project of 0 degrees really from the normal temperature. And what we're going to look for is the best way to model uh, the fluctuations in temperature to see when we hit that 1.5 degrees above that baseline. Some of these are by projecting this critical tipping point, we can prepare for some of the extreme weather conditions we might see, such as droughts, maybe some extreme precipitation. Also can help prevent loss of species and preserve water availability. There are some events that have already been set in motion by climate change. You may have seen, noticed an increase in natural disasters, things of that nature. So the quicker we can identify this tipping point, the sooner we can put in those specific procedures to help mitigate the damage. All right, again, just a little bit about the problem presentation. Uh, this project is attempting to address when that temperature will reach 1.5 degrees Celsius above pre-industrial levels. And then again, like that zero level for the pre-industrial levels will kind of be our baseline or our reference point. So specification and design of this project. So again, the scope is going to focus on world temperature from the late 1800s through 2020. Really a naive model on the prior year's overall data will serve as the baseline, and the results for or of the project will fall into three groups. So we have the data exploration, predictive modeling, visual analysis, and a conclusion. So data acquisition, really the majority of the data used for this project was retrieved from NASA. It's their Global Land Ocean Temperature Index. The land temperature data that was referenced in the proposal will not really be used for any analysis for this project. We'll get into that data in a little bit, but just keep that in mind moving forward. So data exploration, again, this chart on the screen is the data pulled directly from NASA. You can see that it goes back all the way to 1880 roughly. This data was pretty intact. There weren't any missing points or any inaccuracies. And as you can see, it's relatively flat up until 1964. You do see that there are a couple increases in the temperature changes in the 1940s, but nothing really of note or significance, really up until you start seeing that upward trend in 1964. While seasonality really didn't play a part in this presentation or this project, it was looked at briefly just to see if it would make sense to include a seasonality component in the analysis. And really, a couple things came out when looking at this data. First of all, there wasn't really a hard seasonality component to it, just by kind of looking at the temperature changes. You can see here it's broken down by month, and also kind of seasonally, like spring, summer, fall, winter there on the right hand side. See broken down. And really, there wasn't much variance in the average increases. You can see that there is a little bit of a spike in March and February there, but really due to the fact that this is a more broad, we're trying to nail down like a broader date or range of dates in terms of years to determine critical climate change. Really didn't make a whole lot of sense to include some seasonality in this project. So the data transformation, so as we noted in the examination of the data, really there wasn't much of a true trend until around 1964. And then you can see here it kind of takes almost kind of like a linear direction up there in a definite upward trend. Because of this, we omitted all data previous to 1964 when it came to conducting testing for the models. Uh, Really, if we would have included all the flat trend before all this, it really wouldn't have contributed anything of note or of relevance to the outputs. So we didn't want to muddy the waters at all by including that flat data. So theoretical motivation for choice of technique, just due to the type of data that we have, also with what we're looking to accomplish with this data, a time series approach obviously made the most sense since we're looking to forecast out quite a few years. We did incorporate a temporal partitioning of the data to attempt to reduce overfitting. When partitioning the data, we played around with various time frames, such as 10, 15 years, even 17 years, but really 20 years made the most sense. Very early projections in theory predicts critical climate change at least 20 years out. So we figured if we started there, we should be okay projecting the data out. So we did use a 20-year period for our testing region. Again, we did use a naive model as the baseline, and then we used a few different factors to try to project our accuracy or to predict our accuracy. So we used average error, mean absolute error, root mean squared error, and mean absolute percentage error. So iterative results. So we started with the naive model here. As you can see, so what we did, we just used a pretty basic naive model, just taking the previous year's value to forecast the following year. We fitted it to a time series chart, and then the residual error was shown on the secondary chart below. And you can see next to the residual, you can see all the projections for the errors or the accuracy measures. We did this with the subsequent models as well. So focused on models that were built more for trend analysis without a seasonality component. So again, we took this naive model. We also did averages, a trend or linear analysis, and also a Holt's method. So you can see here with the descriptions of results, Holt's method was the best predictor of future results. So you can see the box below with a little heat map. Holt's really came out ahead in the average error, mean average error, and the MAPE. All indicated better results from the holds. We did attempt to use overfitting by not necessarily choosing the best alpha or the optimal alpha. We just didn't want to make it too fine of a point on that. Trend modeling showed the second best results, with the RMSE showing better numbers there. But ultimately, it was Holt's method that set itself apart. As you can see here, the moving average really didn't have much validity to it. I did try a few different numbers, but it just didn't seem to work out or to make much sense to use the moving average. And then you can kind of see it's illustrated here. So we did use 3-year, a 5-year, and 10-year. Ultimately, the 5-year gave the best results. You can see it's still not very accurate. The trend analysis looked at a linear and polynomial equations, and really with this little exponential spike that you see here, if it wasn't for that, a linear model probably would have fit best. But this is actually showing a polynomial line here, just because you can see that it does look like the line's increasing. The polynomial actually gave a better fit for this. But the trend analysis did produce fairly good results. So again, to summarize and conclude, the Holtz method appeared to have the best indicators of accuracy. It's not the simplest model to implement, but it does give the best chance to build an accurate forecast for the critical climate change. And due to that there's no seasonal data, it appears that Holt's method is going to be the best bet moving forward to predict critical climate change. Thank you.